Hi, this is our Chem 112 review for 5th exam, and this is the second segment of our practice exam. Now, the practice problem that I'd like to go over is practice problem number 15. Now, this is on calculation of pH of a buffer, pH of a weak acid. We can give you pH. You need to calculate Ka. So let me write down from pH to Ka. Or we can give you Ka value. You need to calculate pH. So you should be ready for both kinds of questions. So I picked one problem for our practice, which is from book, chapter 16, number 51. This is the Brown and LeMay 12th edition book. Now, this question is about lactic acid. Now, you don't have to know the organic formula of lactic acid. You can write it down as HA. So lactic acid as HA. And they gave you the initial concentration. So initial concentration of HA equals to 0.10 molar. pH is given in this problem, which is 2.44. And the question is asking for Ka value. I want to remind you that Ka is equilibrium constant for acidic reaction, A for acid. So Ka is for acidic reaction. Lactic acid is a weak acid. It's not like one of those strong acids like HCl, HBr, HNO3. So anything other than those acids, most likely they are weak acids. So that's how you know lactic acid is not a strong acid. So since this is not a strong acid, it's a weak acid, it will break down only partially. Out of some hundreds, maybe a few of them would break down into H plus and A minus. So initial value that's given in the problem, 0.10 molar. When you just put that acid in solution, it doesn't get enough time to break down. So it's 0 and 0. At equilibrium, since this is a weak acid, 100% of HA would not break down. Let's assume that only X is the amount that breaks down. So left over would be 0.10 minus X. So that's the equilibrium concentration after X amount of HA breaks down. Now, we need to understand this. If one HA breaks down, you're going to get one H plus and one A minus. You follow these ratio. These are the coefficients of the balanced reaction. When X breaks down, when X of this breaks down, you get X here, X here. So since X breaks down, you get X here and X here. Now I can set up an expression, equilibrium expression, Ka, which will be given by H plus times A minus over HA. And I can plug in all these values, so this becomes X times X divided by 0.10 minus X. So X squared on the top and 0.10 minus X on the bottom. Now, this also gives you pH. That means I do know this value. So let's now calculate from pH to H plus. So pH equals to 2.44. And we know that pH is minus log of H plus. So minus log of H plus concentration. And keep in mind, this is log with respect to base 10. That's how pH is defined. 2.44. So if you solve it to be log of H plus is minus 2.44, then take inverse log or second function log in mini calculator. And that will give you H plus concentration. After doing inverse log of this, it'd be 3.63 times 10 to the negative 3. That's H plus concentration. Keep in mind, H plus concentration is our X in this problem. So we already know that this is the X value. So that means I can now solve it. 3.63 times 10 to the negative 3, that's the molarity. This is the molarity. So square that, divide by 0.10 minus 3.63 times 10 to the negative 3. That's also molarity. Molarity squared by molarity. So I got this value about 1.4. 1.4 times 10 to the negative 4. And the unit is molarity. So make sure you know how to do a similar calculation. So if a weak acid is given, pH is given, you can calculate Ka. Alternatively, Ka is given, you should be able to calculate pH. So you should try another problem like this, where Ka is given and you need to calculate pH. So this is practice problem number 15. Now I'm going to do practice problem number 16. So this is practice problem number 16, and again I picked up one problem from homework, which is 16.73. Again, this is Brown and LeMay 12th edition book. This is the calculation involving pH of a weak base, not acid. Before I go over this calculation, let me remind you about weak bases. Strong bases are hydroxides of calcium, sodium, potassium. All those are strong bases. They break down 100%. Weak bases are ammonia, mostly it's ammonia, or something that you derive from ammonia. I can replace hydrogen, so ammonia is like this. NH, there are 3 hydrogens, H, and a pair of electrons. That's ammonia. I can replace hydrogen by one alkyl group, methyl group. That becomes methylamine. So I can have CH3 here, H. This is also a weak base. Instead of CH3, I can have CH2CH3 or ethyl group. It will be called ethylamine. You don't have to know the name, but what you need to know is ammonia is a weak base, so is this. Instead of writing down these formulas, you can just write down RNH2. R is the alkyl group, in this case methyl group. So I may replace 2 of these hydrogens by 2 alkyl groups. In that case, it will be like this. H, methyl group, another methyl group. Dimethylamine, let's draw a line here. There are 2 R, so it would be R2NH. But in each case, I have a pair of electron on nitrogen. So make sure you know that. In the same way, it could be R3N. These are all weak bases. Now what kind of reaction you'd expect? When they react with water, hydrogen of water is picked up by this nitrogen. So it becomes positive and OH gets separated, and that gives you the basic property. Now let's now focus on this particular problem, number 73. The given information, let me write down the given information in this problem. .075 molar ethylamine, C2H5NH2. Kb value, again this is the equilibrium constant for a base, basic reaction. 6.4 times 10 to the negative 4. Question is, what is the concentration of OH minus and what is the pH value for this weak base? So I'm going to show you this. Instead of writing down C2H5NH2, I'm going to simplify it by writing down as RNH2. Okay, so let's now show you the reaction first. RNH2, where nitrogen has a pair of electrons. Because you know that in this structure, nitrogen must have 8 electrons around. So, reacting with H2O, one of the hydrogens would be picked up by N, so it becomes RNH3 plus and OH minus. Let me write down like this so that it'd be a lot easier for you to follow. I can write down water as H plus and OH minus. H plus, being positive, is attracted to this electron pair, and then it makes RNH3 plus and OH minus get separated. In your solution, if you have OH minus, that would give you a basic property, and that gives you basic reaction. Now let's set up this expression. Initially, they gave you 0.075 molar ethylamine. Water is a solvent. This solvent is usually present in large excess. There was no RNH3 plus or no OH minus at the beginning. At equilibrium, since this is a weak base, a part of this would break down, and the leftover would be 0.075 minus X. That's equilibrium concentration. This is already excess. Minus X is not going to make much difference. It's like you went to a Pacific Ocean and took a cup of water. And would there be any change in the depth of Pacific? Answer is no, because you have so much water there. Similarly, there's so much water here, even a part of that breaks down in this reaction is not going to make a big difference. And RNH3, if X of this reacts, you're going to get X here, X here. Again, it's a 1-1 relationship. One of these would give you one of this and one of this. When X breaks down, it gives X here, X here. So now, this time, equilibrium constant would not be Ka, it would be Kb, because I have a base, OH minus. So I can set it up as Kb equals to X times X on the top. So X times X on the top, and reactant on the bottom, 0.075 minus X. So it would be X squared divided by 0.075 minus X. Now Kb value is given in this problem, so it's 6.4 times 10 to the negative 4. And you can set up this expression. Now there are two ways you can do this problem. One is the most accurate way. You can multiply these both sides by 0.075 minus X and write down a quadratic equation and solve the quadratic formula. Most of the engineering calculators or scientific calculators can handle this kind of solutions, and then they can give you a quick answer. You get two X values, one is positive, another is negative. Positive is meaningful, so that's the only acceptable number. Negative one, you just ignore it. The other alternative is the approximate method. You take a chance here. You assume that this X is too small compared to 0.075 and then solve it. But unfortunately, even though it's going to work in most problems, in this particular case, that's not going to give you a good answer. If I ignore X, if I ignore X from the bottom, then ignore X from the bottom. That means ignore this, then this will be simple math. Then X value becomes, I'm just showing you what I got, which is 6.93 times 10 to the negative 3. And that's OH minus concentration. But question is, you have to see that whether your approximation is right or wrong. You should double check whether what percent X is. So that means you should check, this is checking that X divided by 0.075 times 100. check validity. So we are checking the validity of our approximation. And in this case, this is what I got, 9.23%, which is greater than 5%. So it's not a very good approximation. So you cannot ignore this x from the bottom and get the x value as your final answer, because this will be off. So what you need to do in this case, there are two alternatives. Use your calculator and solve that quadratic formula, or you have to do it in an old method. In old method, let me write down what you need to do. After you multiply both sides by 0.075 minus x, then you can write down an expression like this: ax squared plus bx plus c equals to 0. That's the quadratic formula. And then it would have two values of x, minus b plus minus ba squared minus 4ac divided by 2a. So when you arrange this and write down in this form, whatever numbers you have in front of x squared is going to be a. I may have like 5, 10, or whatever it is. That would be my value for a. Similarly, value for b and c, plug in here, and that would give the x value. Again, there will be two x values. One would be positive, that's acceptable, the other one is negative, and ignore it. So, as I said, in almost over 90% of problems that you have in the book, this kind of approximation would work out. But there is about 10% cases where it did not work out. You have to do in a longer method by solving a quadratic equation. So this is all about practice problem number 16. Now we're going to do number 17. Okay, in number 17, this is a conceptual question. First, I'm going to write down some of the formulas we already have applied. Ka times Kb equals to Kw, which is water dissociation constant, or equilibrium constant for water, which is 1.0 times 10 to the negative 14. This is 1.0 times 10 to the negative 14. pH plus POH equals to 14. H plus times OH minus equals to 1.0 times 10 to the negative 14. Now quite often, these things are quite straightforward. pH, in the same solution you're looking at pH. This is minus log of H plus concentration. This is minus log of OH minus concentration. If you add them up, it should be 14 at room temperature. Quite often we misunderstand application of the stop expression. Let me write down two expressions and so that we can examine whether that's going to give me 1 times 10 to the negative 14. First case, say Ka of H2CO3 times Kb of CO3 2 minus. So if this question is given to you in exam, is it right to write down as 1.0 times 10 to the negative 14? Is this right? Answer is no. Even though you can get a Ka value for H2CO3, Kb of this, but this product is not going to give you 10 to the negative 14 that I wrote down on the top. So what is missing here is this should be conjugate acid-base pair. So if this is the acid, its conjugate base has to be here in order this to be valid. So in other words, this is not right. So let's write down no, it's not right. What is right? Ka times H2CO3 this is H2CO3 times, this is the acid, conjugate acids. Conjugate base, you remember how to get conjugate base? Knock off H plus. That means Kb of HCO3 minus. Now we have a conjugate acid-base pair. Now the product would be equal to 1.0 times 10 to the negative 14. So this is right. And this is wrong. So make sure you understand this kind of conceptual questions. Now practice problem number 18 is on buffer solution. I would like to give you a background of buffer solution before I do a problem. So this is on buffer solution. And by going over buffer solution, I'm also going to discuss what is called buffering capacity. Buffer capacity. So let me go over this, then we'd go over specific problems. First, in order to get a buffer solution, you must have a weak acid and its conjugate base. Now, weak acid could be one of the organic acids. So let's pick this one, HC2H3O2. This is acidic acid. And its conjugate base would be sodium acetate without the hydrogen. So I can write it down as C2H3O2 minus. So this is, I can write down as HA, and I can write these down as A minus. Now how do I make this buffer? I can add, say, 3 HA, just as an example, and 3 sodium acetate. So sodium would get separated, and it would not play any role here. So let's, for the time being, assume that I have a water solution with 3 HA. Let's call it HA, HA, HA. So I have 3 of them, and 3 A minuses coming from, they're all mixed together, even though I drew a line here. So they're all mixed together. And that would give you a buffer solution, because I have a weak acid and its conjugate base, even though I'm bringing A minus by adding sodium acetate. So sodium gets separated, it would be floating around within the solution, but would not play any role here. It's called a spectator ion, and this is the weak acid. Now, this is a buffer solution. Let's test that. If I'm going to add OH minus, if it is a buffer solution, there has to be something that would grab OH minus or react with OH minus so that OH minus concentration would remain unchanged within the solution. So what can react with the OH minus that you're adding from the top? HA, the weak acid. So let me show you the reaction. HA, then hydrogen will react with that, gives you H2O plus A minus. So I'm adding OH minus, then H is going to react. So as if, even though you're adding OH minus, as if there's no extra OH in the solution, because if there's an extra OH, pH would go up. OH minus would increase the pH because increase the basic property. So you're not going to see that because HA is neutralizing that. If I add H plus, there is A minus. That's going to grab H plus. So this is how it's going to happen. So no matter whether I add an H plus or OH minus, there is something to grab it or react with it so that there be no additional H plus or A minus within the solution, so there be no change in pH. The question is, how long can it happen? How many OH minus can you add before it shows any change in OH minus concentration in solution? in this figure, there are three of them. So if I had 3 OH minus, all three would be gone. The fourth OH minus, when it comes down, there's nothing to grab it, nothing to react with. That means that would show up as an extra OH minus, and then pH would go up. So that means it reaches its capacity, and that's buffer capacity. So if I have large quantity of HA or large quantity of A minus, buffer capacity will be larger. That means you can add a lot more H plus and OH minus before pH starts changing. So keep that in mind. Buffer capacity depends upon how much of weak acid and its conjugate base are there in the solution. So now we'd be going over some specific problems. Like in this particular case, if I say that I have 3 moles of HA and 3 moles of A minus and compare it with 1 mole of HA and 1 mole of A minus, obviously 3 mole would have 3 times more capacity than 1 and 1. So there would be a conceptual question like this in exam. So this is about practice problem number 18 on buffer solution. The next problem is this also has to do with pH effect on solubility. This is going to be our practice problem number 19. Now this is pH of a buffer. You save your time if you know Henderson-Hasselbalch equation. So Henderson-Hasselbalch equation is this one. pH equals to pKa plus log of conjugate base over conjugate acid. So that's pH of a buffer solution. Now for this I have chosen problem number 17.21b. And the given information is 85.0 ml, 0.13 molar HX, which is, we're calling it the weak acid, 95.0 ml of 0.15 molar sodium compound. So this is a lactic acid. This is HX is lactic acid. This is sodium lactate, the 0.15 molar. And Ka is given for lactic acid. Equals to 1.4 times 10 to the negative 4. With that information, let's calculate pH of this buffer solution made of lactic acid and sodium lactate. So if you, again, lactic acid is a weak acid, so that it has the composition of the buffer. Now, whenever you have two different solutions added, first you find out the new concentration, because concentration has changed. So this is the formula to use. Volume 1, molarity 1 equals to volume 2, molarity 2. So I'm going to show you one such calculation. Total volume is total, if you just add up those two volumes, I got 180 ml. The total volume is 180 ml. So 85 ml of 0.13 molar got diluted to 180 ml. So obviously HS concentration would be different from 0.13. Let's find out that concentration. So I'm going to write down this expression. M2 will be given by V1 M1 over V2. Now volume 1 is 85 ml, so 85.0 ml Molarity 1 is 0.13, or initial molarity. 3. Final volume is 180. Now ml would cancel out, that gives you molarity. And I got this number for this one, 0.061 molar. So 0.13 concentration has dropped to 0.061 because volume is increased, you added 95 ml of second solution. So this is the new concentration of HX. So this is the concentration of HX. Similarly, you do a calculation for X minus. This is for dilution of HX. Similarly, for X minus, you're going to do this 95.0 ml times, this time the concentration, initial concentration is 0.15 molar, divided by the total volume, which is 180. So ml will cancel out. This gives you 0.079. So whenever two such solutions are mixed together, make sure you figure out first the concentration. This is X minus concentration. So I know the weak acid concentration. I know its conjugate base concentration. I can just plug in into this expression. And I can calculate the pH. So let's do it with those values. pK would be minus log of Ka, minus log of Ka. Keep in mind this is base 10. These are all base 10. Log of conjugate base on the top. Conjugate base is Cb. So that value is 0.079. 0.079 molar on the top. And HX value on the bottom, 0.061. 0.061. So that's we plugged in. So this is the conjugate base over conjugate acid. Again, conjugate base is sodium acetate. That's the base part. Ka value is given 1.4 times 10 to the negative 4. So I got this number minus log of 1.4 times 10 to the negative 4 plus log of this number, log of 0.079 over 0.061. And my answer to this was 3.96. So let me review this. You added these two solutions. First you get the concentration in the whole volume of 180 ml. And first we got weak acid concentration, then conjugate base concentration, and then we calculated pKa, which is minus log of Ka value, and then just add it and use this Henderson-Hasselbalch equation, and we got 3.96. So this is how you're going to calculate pH of a buffer solution. Now we're going to begin with practice problem number 20. This is on solubility and effect of pH on solubility. So this is going to be number 20. So this is our practice problem number 20, and I should first write on the title: solubility, pH, and common ion effect. Ion So solubility influenced by pH and this common ion. So I'll go over one simple example. When you do work on these kind of problems, make sure you have a solubility table in front of you. So silver cyanide is not a highly soluble compound, it's a solid. In water, it breaks down, not 100%, only part of this, giving Cn minus aqueous. Now, here we are going to examine, without doing any math, what influence it would have when I'm adding H plus, because of the pH is there. Now, this is conjugate base of a weak acid. So this is conjugate base of a weak acid. Now think about what weak acid would have Cn minus. Obviously, in order to make the acid, you add H. Cn minus has -1, so only one H can be added. So the weak acid is HCN. Now this is the conjugate base of HCN, and that would like to get back to HCN form. Whenever it sees H plus, it's going to grab that. So whenever you add acid, H plus will be picked up by HCN. Picked up by Cn minus, so it will be like this. H plus plus Cn minus, that will make HCN. Now let's apply Le Chatelier's principle here. In case you need some kind of reminder about Le Chatelier's principle, this would serve as that. Now, if I'm adding H plus, Cn minus would be consumed by H plus. So it would make HCN. That means this will be gone. This concentration will be gone. So that means you're decreasing as if you're taking away one of the products. According to Le Chatelier's principle, in order to make up, system doesn't like a loss from equilibrium. So since it's losing Cn minus, it has to go from left to the right. The left-hand side has solid. Right-hand side have ions in solution. That means solubility is increased. So if you add H plus, in this case, adding H plus means lowering the pH. As you lower the pH, solubility of AgCN is going to increase. So a question like this may be on the test, so make sure you understand this. The next problem that I would like to go over is practice problem number 21. Still we're dealing with solubility. Now I picked this problem from the book number 17.51. So what we're going to calculate is, from solubility, we're going to calculate KSP, equilibrium constant, SP for solubility product. Now, so let me write down what is given in this problem. They gave you calcium fluoride. If you look at the solubility table, it's an insoluble or partly soluble substance. So only part of that would break down to calcium 2 plus, aqueous plus 2F minus aqueous. So initial concentration, let's assume is A. This means when you just put the solid in water, it didn't get a chance to break down. It is 0 here and 0 here. At equilibrium, since this is not highly soluble, part of that would go in solution. Breaking down means going in solution, or that's solubility. Let's assume X is the quantity that breaks down, or X is the amount that goes in water solution, which would be same as solubility. When X breaks down or X goes in solution, how many of calcium are you going to get? When one of these breaks down, you get 1 here, 2 here, and that has to be maintained. When X breaks down, you're going to get X here and 2X here. And that's important, because in this particular case, we're going to get solubility. So let's set up now KSP expression, solubility product, which is also equilibrium constant expression. Calcium 2 plus raised to the power 1, F minus raised to the power 2. At the bottom, ignore this. This is a solid. If a solid mixed with this aqueous solution, just ignore the solid. It's a heterogeneous equilibrium. Or a pure liquid mixed with aqueous, then pure liquid, you ignore that. So now I can plug in these numbers, x times 2x whole squared. So we get 4x cubed. In order to get the KSP value, in this case that's what we're going to calculate, KSP, we must have the x value, or solubility has to be given. But in this problem, indeed, solubility is given. So let me copy that number. So solubility given in this problem equals to 1.24 times 10 to the negative 3 molar. Solubility means maximum that goes in water solution, which is X here. X breaks down means X goes in water solution. So this is X. So now just plug in that value here, the 4 times 1.24 times 10 to the negative 3 cubed. And that gave me 7.63 times 10 to the negative 9. So that's the answer to this question. So from solubility, you'd have a question like this, where KSP, you need to calculate KSP when solubility is given. Or I can also ask you to calculate solubility when KSP is given. So either way, I mean, you should be ready to do this kind of problem. Now we're going to do practice problem number 22. This is also on solubility, but here KSP is given. And we're going to do 17.60 B. As a 12th edition book. So here KSP is given, and you need to get the solubility at a particular pH. So KSP is given, you need to get Cal. So here, in this problem, you need to get solubility. So let's have a question mark here. Now this question on 60B deals with nickel hydroxide. Nickel hydroxide, that's a solid that breaks down into nickel 2 plus aqueous plus 2 OH minus aqueous. Now they gave you pH equals to 10.0. Now first we need to understand that what pH has to do with this solubility. Here, having H plus means also you have OH minus in solution, because H plus times OH minus has to be 10 to the negative 14, or pH plus POH will have to be 14. So first find out how much OH minus you have. POH will be given by 14 minus pH. So that means 14 minus 10, that gives me 4.0. From here, POH means minus log of OH minus equals to 4. So OH minus is equals to 10 to the negative 4 molar. Now that's the common ion coming from pH. And that common ion is going to increase this, shift it to the left. In other words, it's going to make some changes in this equilibrium. Now let's now calculate the solubility. So initially, say I have quantity A. We don't care about it, but still for understanding, we assume that. There's no nickel 2 plus. OH minus will be coming from the pH of the solution. So 10 to the negative 4. It's coming from pH. So don't forget, it's not coming from breakdown of this, because it didn't have chance to break down. At equilibrium, a part of this would break down, so leftover is A minus X. Now again, if one of these breaks down, you get one of these and two of this. So if X breaks down, you get X here and 2X of OH minus. Now I can set up an expression of KSP. Again, I'm going to ignore the solid, so it'd be nickel 2 plus raised to the power 1 times OH minus raised to the power 2. That's the coefficient of the balanced reaction. And at the bottom you have solid, so we ignored the solid. So this would have X, this is nickel 2 plus is X, times 2X plus 10 to the negative 4. So you can write down 10 to the negative 4 plus 2X. Now you can assume that X is very small compared to 10 to the negative 4. So I can approximate this. As I said, in most cases it works out. In this case it would work out. So it would be X times, oh I forgot to square this, so you must have square of this. So X times 10 to the negative 4, I ignored this X square. So that gives me X times 10 to the negative 4. Now we already have the X value from this KSP. In this case, we have either the X value is to be given or KSP has to be given. So if I have KSP given, let's assume that KSP is given. I think in this problem, KSP value is given. 6.0 times 10 to the negative 16. When this is given, I can solve it. X times 10 to the negative 4 square, and that would give me X value equals to 6.0 times 10 to the negative 8 molar. So at this pH, pH 4 or pOH 4 or pH 10, solubility, this is solubility. Solubility is 6.0 times 10 to the negative 8 molar. So this would be the end of our second segment of this review session.